Jorge Lira from the mathematical department of the Universidad Federal do Ceará. He's going to speak about Einstein type elliptic systems. When you wish.
Thank you, Paco. Thank you for the invitation. Thank you, Miguel. I have to say hello for my friends in Granada. It's a pleasure to be here, but virtually this time. So I'll just present some slides about this topic that was mentioned in the title, which is a sort of invariant or variant, say, of Einstein equations. So you have, of course, the well-known equations for the general relativity, and are just trying to address questions related to, different types of the same sort of equations. Can you start, Paco, just sharing the screen? Do you think it's just a moment? Maybe just like that. Can you see the screen?
Yes.
Okay. So this is the title, Einstein type elliptic systems, to suggest that the systems of PDEs that I'm going to show you is related to the Einstein equations. And then this is a joint work with Rodrigo Avalos, which is a postdoc of mine here in Fortaleza. And just to recall some basic facts, some terminology from this set of equations from relativity. The geometric setting I would consider here is some Lorentzian metric in some manifold V. So V is that n+1 dimensional manifold. And it has this Lorentzian metric that can be splitted into a Riemannian part and some timeline given by this factor R. So have the splitting M cross R as being V. Is that model that I'm going to consider from now on. So G bar is the metric in this whole Lorentzian ambient. And the Einstein equations can be written down in terms of this metric, like that expression, which involves the well-known Einstein tensor, which is the Ricci tensor of the metric minus half of the scalar curvature times the metric itself. That's the left-hand side, which is geometric in nature. This is the geometric content of the Einstein's equations. And on the right-hand side, you have this T, which is the energy momentum tensor that can be understood as the physical content of the equation. So the geometry could be located in the left-hand side, say, and the physics, the physical description of the problem, or the content of matter, energy, radiation of this universe, which is V, is in that right-hand side, is encoded in that right-hand side. So there is the interplay between geometry and physics. You can explain physics in terms of geometry and vice versa. That's the classical statement of the Einstein field equations. So T can be built up from different sources of matter. Usually you consider for like a toy model, the vacuum, which means that you consider T equal to 0, and then you have basically Ricci flat matrix in that ambient space-time. V is the space-time is exactly because M corresponds to the spatial dimensions and R to the time dimensions, say. So in that work, you can consider different sources which are not vacuum, are actual sources of matter, like some scalar field. In that case, you just consider some real function in V, like a real potential. And then T is given by that expression, which is quite familiar from people that work in harmonic maps. So you can just consider this T tensor given, originated by the scalar field phi. Or you can consider some sort of fluid in that V. So V is filled up with a fluid, and this fluid has some pressure, some density, and some velocity. So you have the density of mass of that fluid given by me. The pressure of that is given by P, and the velocity of the particles of the fluid is given by U. So that's another possibility of considering this sort of general matter given by that fluid. Other possibility that we are considering for now on is the electromagnetic sources. In that case, you have two forms. These two forms is related to the Maxwell equation. So it's the electromagnetic field F that encodes, that absorbs both electric and magnetic sides of that field. They are, of course, intertwined in that two form F. And the components of that form give you the electric field, and other components give you the magnetic field if you have some sort of gauge, some sort of choice of coordinates. And for that two form, you can choose that tensor field T. The tensor field T related to F is given by that expression. So different kinds of matter, different kinds of fields, give us different choices of T. That's the idea. And you can even sum up these contributions from scalar fields, fluids, and electromagnetic sources in that general accommodation of different kinds of matter, which is natural, is more realistic than vacuum. And then, for instance, you can consider, for our purposes here, the T that comes from that combination of electromagnetic sources. That's the part of the tensor given by the influence of this electromagnetic field, and the fluid. So the fluid has a density of mass, so me, you be the mass density of this fluid, but this fluid is charged. Each particle has some charge, so there is some field generated by this distribution of mass in that universe. That's the, say, geometric physical scenario we're considering here. So in that case, the Einstein equations is no longer G equal to 0. G is the Einstein tensor, so reach minus half times scalar curvature times metric. So G is now something given by that field, which consists of that fluid of charged particles. Well, the T has some property in order to be linked with the Einstein tensor. The Einstein tensor is divergence free, so T is also divergence free. So you have no divergence for T. You have that expression that is a kind of way of stating that T is conserved in some sense. There is an infinitesimal conservation law related to T. So that pair of equations is the Einstein-Maxwell field equations, in the sense that you have both geometric content given by G as well as physical content given by T. So Einstein-Maxwell equations, I refer to being these equations you can see right now. So there is a list of equations which can be read and deduced from this pair. The first is that G, I just writing down here the special description of T. T is given by that expression on the right-hand side of G in the first equation. You have some sort of Maxwell equation here. So we have the pair of Maxwell equations, which is familiar from the electromagnetism, the classical electromagnetism. So we have the pair of Maxwell equations. So the first three equations correspond to Einstein equations and Maxwell equations. So that's why you call the system Einstein-Maxwell. And you have some sort of conservation of charge. So that divergence of me times u means that I have that conservation of charge electric charges here in that framework, and you have some sort of law of motion. That last equation tells us that the particles travel along, geodesics, but geodesics affected by the tensor field given by the electromagnetic source. So this is the Lorentz law. In fact, the particles are accelerated, and the acceleration is caused by the presence of F. If F is turned off, so you have just geodesics in this space-time. That's the way you can absorb the law of motion in the field equations. So this is a consequence of the field equations. So in fact, the most important equations here are the first, second, and third one. Well, in order to solve that problem, the problem is to find a Lorentzian metric, G bar, that solves that system. So G bar should be given in such a way that it solves all of these constraints here. But that's a challenging task because, of course, if you can write this in coordinates, local coordinates, you have some hyperbolic system. And the idea is to, in certain way, reduce the problem to elliptic system. That's why in the title it state elliptic system instead of hyperbolic system. How can you do that? It's the initial value formulation, the Cauchy problem for that system that give us some hints of how to do this reduction to elliptic system. The idea is to write the equation of the system of equations in normal form. So you can consider the parameter t, which is time, and take the second derivatives of the metric, the ambient metric, and try to write all of the equations in terms of some nonlinear D'Alembertian operator acting on the metric. That's the first part, to write the system in a normal form. The second one is to consider the splitting of the geometric quantities in terms of that M cross R decomposition. You have V, which is the total space-time, and you break up this into a space, say leaf, M, and some R, which corresponds to the time dimension, as I said before. So the task is to write all of the geometric and physical tensors in terms of that decomposition, to see what could be the spatial components, the time components, say the temporal components, and the mixed ones. That's the idea. So you can start just noticing that if you can see G bar as something that evolves in time, that's the idea of the first equation, that you can see the acceleration of the metric. The acceleration of the metric in terms of the time t, is given by some hyperbolic operator. Then the idea is that since you have the acceleration of the metric, the natural thing is to choose initial conditions, the initial value of the metric and the initial value of the derivative of the metric. So you can have zero order and first order conditions given as initial conditions, and with that initial conditions you can evolve G bar in time in such a way that that evolution respects this PD here, the system of PDEs, which is written here. So that's the Cauchy problem, given nice initial conditions and try to evolve that conditions in time to give us the solution of the problem, the original problem. The idea is that you fix some initial metric in the leaf M, and you can write, as expected, the first derivative of the metric in that time t0 as the second fundamental form of the leaf M. So essentially, given thanks to this expression here, you can relate the first derivative of the metric in terms of the second fundamental form. K, the K tensor in that last equation, is the second fundamental form of the leaf M. So there is the interplay between derivatives of the metric and second fundamental form. Then the idea is to prescribe both, prescribe the metric and prescribe the second fundamental form of this manifold M. That's the picture, basically. You have V, we hope to construct V from M. M is that given initial abstract manifold. You have some abstract initial manifold M. In that manifold M, which is Riemannian, is no longer Lorentzian, is Riemannian. In that initial manifold, you consider a metric, some initial metric, say G, and you consider some tensor, which is formally the second fundamental form. If you can build up this space-time and you can embed M into this space-time, so this formal tensor K will be the second fundamental form of the immersion. But from the beginning, you just have two formal tensors, the metric and K. As you know, you have to check if J and K satisfy compatibility relations like Kodadzi-Gauss equations. Otherwise, you cannot have this embedding. So the necessary conditions for having this embedding is to check the compatibility equations from Gauss and Kodadzi. Then the idea is quite simple, but it's quite efficient too, is that you can combine the Gauss-Kodadzi equation that permits to see if J and K satisfy the compatibility equations. You combine those equations with the Einstein-Maxwell equations. Einstein-Maxwell equations have to do with the Ricci tensor, the scalar curvature, and the energy momentum tensor. The idea is to write all of these tensors in terms of spatial coordinates and time coordinates. Then combining the field equations and the Gaussian-Kodadzi equations, we can obtain, for instance, this pair of equations in the bottom of the page. So in order to satisfy at the same time the constraint given by the compatibility equations and the field equations, in terms of the spatial components, you have these two constraints here. The first one says that the scalar curvature of the intrinsic metric is related in some nonlinear way with the second fundamental form. So this K squared is the A squared in our notation as geometers. You use most of the times A instead of K. So K is the extrinsic curvature or the second fundamental form. And this is the squared norm of A, the squared norm of the second fundamental form, the Weingarten map, if you prefer. And that's the trace of the second fundamental form. It's the trace, which is, of course, the mean curvature. So the scalar curvature is linked to the mean curvature and the Weingarten map in that nonlinear way here. 0 corresponds to a special choice, a particular choice of the vacuum. 0 here means that you are considering for the time being just T equal to 0. There is no matter, there is no radiation, there is no energy, just the vacuum. In that case, even in that case, the equation is highly nonlinear in the sense that you have the scalar curvature gives in terms of these quadratic expressions. So K satisfies another equation, which is the momentum constraint. And this express the fact that you have some sort of divergence-free problem here. So the divergence of the second fundamental form is given in terms of the derivative of the mean curvature. It's a kind of is a contraction of the Kodadzi equation, in fact. So you have, sorry, you have Hamiltonian constraint. There is some nice justification for that name, but this is the energy, the Hamiltonian behind the second, the Einstein field equations. That's the Hamiltonian constraint, the first one. The second one is the momentum constraint. So you have a scalar equation and a vector equation. Both have to be satisfied in order to have that immersion of M into V. You should construct V. V is not given from the beginning, but if you construct V appropriately, so you have a space-time that obeys the Einstein field equations. But that's just for the vacuum. Well, the striking result for that is given by Choquy-Bruhat and other people that followed the first results from her. You have basically that reduction of the problem to solving that constraint equations. If you can solve them for a given initial manifold, there are very miraculous things happening after that. If you have the constraint satisfied for the first initial manifold, and if you are able to evolve the metric into time and construct V, for each slice, for each time slice, the constraints are also satisfied. So if you start with a given initial data that satisfy the constraints keep being satisfied for all the time slices in that V model. So the way of doing that is given by the Shukibura fundamental theorem. We have to impose some decay conditions, some control in sub-level norms of the data, but it's just the technical stuff here. But the conceptual idea is that one, to fix a gauge, that means splitting the problem into spatial and time coordinates, as I said before, writing down the PDEs in terms of a normal, say, form of presentation, and try to combine Einstein field equations and Kodai's and Gauss equations to get the constraint equations that are the main part, the core of the problem we did. So that's the gauge permits to write the equations in terms of two fundamental quantities. If you have the temporal vector field that crosses M transversally, so you have observers, say, crossing that space leaf transversally, so you can split that temporal coordinate into two parts, which are like degrees of freedom for the problem. You have the tangential component, which is the shift, is like a tangential diffeomorphism that we are creating from this vector field delta t, and the perpendicular component is given by the lapse. So you have a scalar function n, you have a vector field beta that are part of this temporal vector field delta t. So just to fix in some notation, and from now on you consider that splitting M cross R, so you have to start with M, and in M, into M, you consider a vector field beta and a function N that give us the way how to follow in that transversal direction. If you collect the informations from beta and N, you can reconstruct, say, the time-like direction and then to evolve M in time. That's the, broad speaking, is the idea. So there is a plethora of results and different new perspectives opened up by the Shukibura theorem. We have a very huge, massive literature on this subject. But now you are considering that particular case of Einstein and Maxwell equations, just going back to the original framework. So you still have in that scenario, the constraint equations in the left-hand side here, and they have now not no longer zero, but I have these two guys here that correspond to the matter and energy content given by the electromagnetic source created by this cloud of particles that are charged. So have this dust, this say fluid, more precisely have the fluid of charged particles that create that electromagnetic source, and the influence of that is given in this right-hand side here, which are the components of the tensor, the energy momentum tensor. Epsilon is a scalar density, say, is given by the projection of the energy momentum tensor in that normal direction. And J is a kind of current, which is a vector field or a one form, it's up to you. And then T is the time and the spatial mixed components of the energy momentum tensor. These guys appear now on the right-hand side, so I have to deal with these like given sources. You have these sources, you have to deal with that problem now. So instead of only two equations, you have to also consider the constraints given by or imposed to the fields. Before you had just the constraints given by the geometry of the problem. Now you have constraints given by the physics of the problem too. So you add this third equation to the problem. And the idea to tackle this initial value formulation problem is to change appropriate background metrics, background choices, and then to reduce the problem to some conformal change of metric. So this is the idea dating back to Lishnerovich and the work of Shukibura. So instead of trying to guess what should be the metric, so you have to find the metric G here to solve that problem. Instead of considering any choice of metric, you reduce the possible choices to conformal changes of metric. So you start with some background metric gamma into M, and then you have to find the appropriate conformal factor in order to change conformally that metric into G, and the G is the expected, is the metric you want to find. The same thing can be done essentially for the second fundamental form. That's the convenient splitting used in the literature. K is the second fundamental form. You have here the trace part of the second fundamental form, which is the mean curvature. Tau is the mean curvature, or the sum of the principal curvatures. And this K tilde is the traceless part of the second fundamental form. And the traceless part is split into these X and U. U is the part which is not related to diffeomorphisms, to Lie derivatives of and X is the part of the traceless second fundamental form that comes from diffeomorphism, say. So that's the natural splitting of the traceless part. So remember that you have in the end, the variables now are phi, which is the conformal change of metric. So you have to track the problem in terms of trying to find phi, tau, which is the mean curvature, and U and X. So basically, you can reduce all of the equations to trying to find the nice PDEs from these objects now. So that's just to fix notation. That's the conformal killing operator, which is written down here. And U is the guy that is divergence free in that decomposition of the second fundamental form. So you have then the combination of the Gauss-Codaz equation with the Einstein-Maxwell field equations, and that combination and the choice of this conformal gauge, this conformal change of metric, give us in the end these two PDEs here. The first PDE is scalar PDE in terms of phi. Remember that phi is the conformal factor. So the first term is the Laplacian of the conformal factor in the background metric, in the original metric gamma, which is not necessarily a solution of the problem. It's just a given, a suitable chosen metric for M. In terms of that M, you have the Laplacian of phi, which is the conformal factor. You have the scalar curvature of this original background metric. And you have all of the terms that are given by the geometry or the physics of the problem. So you have the traceless second fundamental form. You have the mean curvature here, tau squared in case. And you have epsilon, which is the density related to the physics, related to the source of matter that we're considering here. And the second equation is a vector equation. X is a vector. X is given by the Laplacian of X is the conformal Laplacian, which is written here in terms of the conformal Lie derivative, the conformal killing operator. So that's the conformal Laplacian of X. And again, you have some information coming up from the geometry, which is the mean curvature, the derivative of the mean curvature, and J. So if you don't have J is 0, like in the vacuum case. If you have some constant mean curvature initial surface, both terms vanish, so you can reduce drastically the complexity of the equations. But in our case, neither we can consider G as being 0, nor you can consider necessarily tau being constant or even 0. So you are trying to face both problems, trying to keep tau as non-constant, even far from being constant, and J as being no 0. So you have to consider non-vacuum scenarios. There are some technical choices here, like each time you can just change conformally that data. So for instance, instead of consider J itself, you can consider that modification of J given by this tilde J, which is like multiplying for the suitable conformal choice. So even every time you see this tilde, that means that we are just modifying the original data by some conformal factor in front of it, multiplying it by some power of phi, which is the conformal factor that is changing the metric. So, for instance, in the CMC case, in the constant mean curvature case, you have that reduction of the metric, the equation. So you have that very nice momentum equation here, because you erased the derivative of tau, of course. So you can see that the problem here is given gamma, which is the original metric, given some mean curvature, given that divergence-free part of the traceless second fundamental form, and given the matter information by epsilon j, given that data, you have to find phi and have to find x. It's like a mapping. So that 5-dimensional choices give us by solving that problem here, that system here, give us phi and x. With phi and x, you can reconstruct the second fundamental form, because the second fundamental form has tau, which is the mean curvature, has u, which is that divergence-free part of the traceless second fundamental form, and you have now x coming from that second equation. Plugging these, joining these parts, you have the second fundamental form, and considering gamma and phi, you have the new metric on M. So you can start solving the constraint equations, and by some sort of variant of Schoenecker result, you can extend this metric into space-time as some sort of a slab, which is the space-time around M. So that's the problem in the CMC case. The first problem, of course, is to ensure that you can have solutions for that non-homogeneous equation here. So we have to consider the kernel of that operator in order to have solutions from the second equations. So you have to characterize the kernel of that operator, and that kernel is given by conformal Killing fields. That's the nice news here, that you can understand quite precisely the kernel of the second equation, which is more linear in nature than the first one. The first one is the really complicated equation, but the second one you can understand at least the kernel, and then you can search for conditions in the original metric in order to rule out the conformal Killing vector fields, and then to be free of kernel, and then being able to solve the second equations. So that's the analytic framework we have to consider now. So if you are back to let me just be back 2 slides here. That set of equations can be written in terms of some Laplacian plus some very complicated terms. That's the structure, roughly speaking, of these metrics. You have the Laplacian of 2 quantities, phi and x, and you have that complicated thing that depends on powers, on the conformal vector field, that depends on the data, etc., etc. You can abstract this just to consider that, for instance, the Lichner-Overich equation, the first equation, or the Hamiltonian equation, is given by the Laplacian of phi in terms of something which is complicated, but is formally written in terms of powers of phi, and some expressions A that depends nonlinearly on the data. So, so you have that equation, that theorem, which is general. It concerns that sort of equation that states that written imposing this condition on the behavior of the metric. So this kind of equations, sorry, has solutions if you can prove that there are sub and super solutions for the problem. So if you can construct sub and super solutions for that problem, which are bounded and bounded by some positive number, then that equation admits a positive solution. Positive because you are searching for some conformal change of metric given by phi, so phi has to be positive. So the tricky part is, in fact, to construct the sub and super solutions. If you have that, then you can use some sort of fixed point argument to find the solutions. And the idea is basically that one. The Lichner-Rovich equation, the Hamiltonian equation, which is the first one, has kernel. And it's hard to manage with that kernel, but then you can shift that equation by some appropriate choice of A. You add this A artificially, but just to have now some equation, some new operator that is invertible. So then you start shifting that operator by some A. You have the sub-solution as the first step in this iteration. So the idea is to iterate, to approximate at each iteration the problem, the solution of the problem, starting from some given initial say choice of phi. The natural one is the sub-solution. If you have the sub-solution, then you can consider that as the first step. Then you plug this phi in the say in the right hand side. So remember that the right hand side is some sort of f, a complicated f that depends on phi. But now we have f minus a because you add this a, this factor a to the operator. So plugging that choice of phi into the right hand side, since a is chosen in a very delicate and suitable way, that expression permits to solve the problem. Now the operator has no kernel, it's invertible, say, and then you can find the new step, the new function. So starting with some phi n, you can just consider the next, which is phi n plus 1, is being the solution of the problem. Then you start this process again by iterations. The idea is to, of course, to find a fixed point of that as a limit of this process. That's the very classical idea. And the points that at each iteration you have to keep each one of these choices, each one of these functions in the same range between L and M. So you have to guarantee that at each iteration you are not away from this slab. That's the challenging part. So you have to be confined in this region between the sub-solution and the super-solution in order to have the next iteration. If you lose that information, so there's no way to pursue to proceed with the next iteration. But doing that, guaranteeing that you have these, say, a priori estimates from the height in some sense, then you can have a priori estimates for the other derivatives, the first derivative, the second derivative, and so on and so forth, even in the weak sense of sub-level spaces. And of course, if you have some sort of compactness due to the estimates, then you can pass to the limit. This means that you have that sequence by iterations. That sequence is strapped between, say, L and M of phi minus and phi plus. You have higher estimates, you have gradient estimates, you have all of the necessary estimates to pass to the limit, in the sense that you can extract a convergent subsequence to some phi, at least in a very weak sense, but phi is the promised, the possible solution for that problem. So the idea now is to make some regularity process to get an actual solution phi with the right regularity, like being a WP solution, etc. So that's the program in moral terms, say just the steps to proceed with the solution. But then you are reducing the problem to find the sub and super solution. So have to isolate criteria for have to propose some criteria to prove that there exists both sub and super solutions. So one of the most prevalent ideas is to consider the Yamabe invariant of the matrix. So in each case, if you have, say, the minimal hypersurface, so mean curvature equal to 0 in the beginning, if you have that part of the second filter form given by 0, so you have the possibilities of existence of super solutions in each scenario. If you have a positive Yamabe invariant, null Yamabe invariant, or negative Yamabe invariant. So that's the classification in the case of vacuum. This means you are not considering densities epsilon and j, You have just vacuum and CMC case. That's the table for existence and non-existence results in that context. But the idea is exactly like I told you before. Try to make the iterations and to prove that at each iteration you have the control of the height in order to get the limits of the process. But that table gives us information about when you have sub-sub solutions, when you do not have. Well, this can be made for compact manifolds M or for non-compact manifolds, but non-compact manifolds which are asymptotically Euclidean, etc., etc. So in our case, you have to consider both non-vacuum and maybe some non-CMC configurations. For do that, you use you are inspired strongly by the works of Maxwell, David Maxwell, and Host and collaborators. So that are the main references you have for doing our calculations. Okay, so the idea then is we start with these, say, the first choice of conformal factor. Then you start with, say, some phi bar, which is a given first possibility of that conformal factor. You try to solve the second equation in the row, which is the momentum equation. So you start with that choice phi bar that could be, for instance, the sub solution. Then you solve the second equation, which is the momentum. And then you plug all the informations coming from that second equation, which is, for instance, the x, which is part of the traceless second fundamental form. You plug this into the first equation, and they try to solve the first equation, which is the most difficult one, which is the Hamiltonian constraint. So M here denotes the momentum operator, say is the second equation, and H denotes the Hamiltonian operator, which is the first equation. So that's the program. And then try to do this in iterations in order to get a fixed point. So start with some phi and end up with the same phi. That's the aim. Okay, let me just I'll split some. I'll just skip some slides in order to be more quickly here. And then the framework we are considering is that either M, our M, which is the initial surface, is compact. That's a possibility. Just consider that M is compact with boundary maybe, or asymptotically Euclidean. So if M is not compact, you consider that M has ends, and each end is diffeomorphic to some Rn minus a ball, a large ball, say. And then at each end, you have a metric that is Euclidean, is approximately Euclidean in a very precise sense, which is here. The difference between the metric in the infinite and epsilon is given by something which is, say, quite small in terms of Sobolev norms. So you can see intuitively that you have different ends, and each end is approximately Euclidean. In our more general result, you also have a compact boundaries. You have different components of that boundary of M, and each component is compact. That's a possibility of extending the results to manifolds which have boundaries. So just to recall you about the results, I mean the equations, you have now 3 equations. Remember that the first is the Hamiltonian equation. The second is the momentum equation. Both are part of that combination of Gauss-Codazzi and Einstein-Maxwell equations. And the third one is a very particular way of writing down the Maxwell equation, say. So for reducing the problem in terms of the electromagnetic field to this scalar problem here, you have to consider some kind of Hodge decomposition or some Helmholtz decomposition of the electromagnetic field that's the thing that's written down in the last line. We start with the electric field. The electric field is part of this, the two form, which give us the electromagnetic field. So have F, which is the electromagnetic field. You have the electric part of that, which is a vector field E. And that E is written in terms of some exact and the co-exact components. So you have some sort of Hodge-de-Haen or Helmholtz decomposition. So that F is the F that appears here. Using that variant of the Helmholtz decomposition, you can reduce all the electric part of the system, say, for all the Maxwell part of the system to this scalar equation here. So that is crucial to have now 3 Laplacians. You had 2 in the classical setting I showed you before, in terms of phi, which is the conformal factor, x, which is part of the traceless part of the second fundamental form, and f, which is now the potential, say, of the electromagnetic field. And then we can read f as a kind of scalar potential for the electromagnetic field, basically. Besides f, x, and phi, notice that note that phi, x, and f are the variables now, of course. And then you have data. The data are listed in these 6 objects here. The data concern the density of mass, the density of charges, the mean curvature of the leaf, the U part of the second fundamental form, and now this theta, which is part of the electric field. So have plenty of data coming up from the physical and geometric, say, information we have, and the variables which are phi, x, and f. That's 12 is the system we have to consider. And the system is scalped in the sense that there is no way to say consider these equations as separated. Each term, each equation in the system is influential in the other 2, because you have information from the third one in the coefficients of the first 2. There's no way to decouple the system unless you reduce the problem to the vacuum and to the CMC case. So there's no way of considering equations separately in that case. It's highly uncoupled system. So in order to get that strategy of modifying the first iteration and trying to consider new iterations and approximations to the actual solution, you have to use the maximum principle. It's more or less natural because since you have to be sure that each iteration give us some function between the 2 sub and super solutions, the idea is that there is no way that one of the solutions can say be tangent to the sub and super solutions. You have some sort of a need of a maximum principle here in order to have that control on the height. Maximum principle is quite useful to have height estimates, of course, for one hand, and on the other hand, maximum principle is a kind of measure of invertibility of the operator. So you have to impose some conditions in order to have a maximum principle for the operators you are considering, especially the first one, which is the Laplacian of the background metric gamma. And the idea is that there is no hope to have a maximum principle for the original operators. Then you have to shift the first operator at least. The second operator, which is the conformal Laplacian, has no kernel. It obeys the maximum principle because you are ruling out the possibility of having conformal Killing operators. Maybe you remember that the kernel of the conformal Killing operators is given by conformal Killing fields, imposing that condition that P is greater than N. Imposing that condition, you can get rid of the conformal Killing fields. So there is no kernel for the second operator. So there is no need to shift the second operator, but the first one has to be shifted because there is no hope that this obeys the maximum principle. So you have to consider this modification of the first operator, the operator that appears in the Hamiltonian constraint equation. So A has to be chosen in such a way that, of course, you can always find a that permits to have this isomorphism, this no kernel configuration. But the point is that if you are not careful about the choice of A, there's no way to control the iterations. That's the trickiest part of the result. At the same time, modifying the operator in order to get invertibility, but not destroying the height estimates that permits to make the iteration work. So there is another problem, that is to control the information at infinity. So since you are no longer have just compact manifolds, you have to impose some conditions at infinity. You have to prescribe the behavior of the conformal factor in infinite. So fortunately, there is a possibility of trying to model the behavior of the conformal factor at infinite by some harmonic function in the ends. There is a way of prescribing some harmonic function, omega, that has the nice behavior at infinite and that contains all of the information of the conformal factor at infinite too. So each time you state the results, you consider that omega, that is the harmonic part of the conformal factor that encodes all the information about the boundary data of the conformal factor, and at the same time the asymptotic behavior of this conformal factor at each end. So omega is that harmonic component of the conformal factor that encodes, that absorbs all of the information about the boundary components and the ends. So then this omega appears here as being the harmonic part of this conformal factor. Remember that a phi is the conformal factor you are searching for. Omega is given by that lemma, so there is a possibility of finding that omega. So the equation reduces to finding this phi, which is, say, the non-harmonic component of phi. So now this modified phi here is the variable you have to find, and the operator, that huge operator, which is Lishnerovich momentum, and the Maxwell equation say that huge operator is just denoted by this p. So p starts with these variables, and then you compute the Laplacians at each one of these data. The conformal Laplacian here in the vector field X, and the usual Laplacian of the metric gamma, which is the background metric for the first two. So that's the say the principal part of the operators, and that nonlinearities that appear on the right hand side are this F. So the system 12, which is that one, have three Laplacians and a lot of complicated stuff here. The system 12 is written in terms of this guy here. So this is a very, it's just a notation, but F is quite complicated. But the idea is always like that. You start with some particular choice of phi here, and you try to place some sort of fixed point argument here, some iterations in order to get that fixed point. It's not that simple, because at each time you have these, you have to guarantee two things, that the conformal factor is always in that range, as you commented before. But another thing is problematic here, is that at each iteration, the informations coming from F and X affect the first equation that is related to phi. So that can be very complicated. But the program is that one, is to control each iteration and not to destroy that compactness of the estimates for phi. Otherwise, there is no way to solve this. Okay, just reaching the end here, but the key point is, again, to construct super solutions for the problem. Now there is some it's more subtle here, because the definition of super solutions is the same formally, but now you have to guarantee that super solution works for every F and every X. Notice that if you have F and X coming from the second and third equations, this F and this X are arguments for the coefficients of the first equation. So the sub-solutions have to refer to these both data here that come from the third and second solutions. But you have to control f and x in a uniform ball. That's the delicate point. The global solution has to be valid for all f, for all x in that ball. So have to control the radii of that balls and to have some sub-solution that is strong enough to be valid, to be a sub-solution effect for each choice of f and x in that ball. So there is a control which is needed for the size of f and x. So you have to solve the equation for f, you have to solve the equation for x, but you have to control the radii in some sub-level spaces of the norm of this data in order to plug this into the coefficients of the first equation, and then to ensure in the end that the solution you can provide by iterations converge to something which is positive, otherwise there is no sense in that solution. And then the delicate part is to keep phi in that range of super solution. So that's the abstract theorem in the sense that you can do this every time you can show you a super solution. If you have some guarantee that there exists a super solution is strong enough in order to be persistent for each f and x in that ball, then morally you can solve the problem. So this means that you can find phi, f, and this should be x, not y, sorry. You have phi, f, and x that solve the three equations, but you have to guarantee that there exists some super solution that more precise and that more restrictive sense. So this is a meta theorem, in fact, because this implies that you have to search for super solutions. There is some technicality here, which is keeping control of these estimates at each iteration, but you can do this with some pain, but it's possible. It's a painful process, but it's finite, so you can in fact prove that the iteration scheme works, and then I can just skip these. Then you have two maybe nice configurations when you have the existence of sub and super solutions granted. This means that you can start with nice choices of say phi minus and phi plus, the sub solutions of the conformal factor, but in such a way that these sub solutions are valid for each iterations, for each f, for each x that come from the coupled equations I have to solve firstly. The first possibility is when we have Yamabe invariant positive, even in the case when you have a very large, say, mean curvature. There is no need of imposing that the mean curvature is constant or zero, say. We can consider far from CMC case, but you have to impose that that condition on the general background metric. So we have an initial metric gamma on M, which has a positive Yamabe invariant. In that case, choosing that condition here, that weight, you can rule out the conformal Euclidean Laplacian kernel, and then you in that way you can consider mean curvature, second fundamental form U, say these two guys tau and U give us the second fundamental form essentially, because this gives us X in the end, which is the third part of the second fundamental form. You have some F, which is the electromagnetic field. You have some density, and you have some mass density and some charge density with these guys here, which is geometry, second fundamental form, and the physics, which is the electromagnetic field. In that case, you have a solution for the problem. But you have to impose the positivity of the Yamabe invariant. The other possibility is you do not have that, so you have a non-negative, non-positive, say, Yamabe invariant, but in that case, you just impose that condition of you have a small mean curvature, not necessarily constant, but small. In that case, again, you impose that condition. You have all the data, but this time these guys are small. Then in this case, you have also the conformal, the solution for the conformal problem. That means you can solve the initial value equations, and then to guarantee that there exists, at least for a short time period, there exists a solution for that Einstein-Maxwell field equations. So this is just a comment about the boundary conditions. You have to impose marginally trapped boundary conditions in order to mimic the evolution of black holes in that geometric setting, but I can skip this just to make the final comments. All of these efforts, in fact, are motivated by another program. The program is to try to see if you can extend to push these methods by Choquet-Bruhat, David Maxwell, James Eisberg, if you can consider that sort of models for dealing with strongly coupled equations. And the purpose was to see if the equations are coupled, there is no way to uncouple, to decouple these equations. Is it still possible to apply the methods, the classic methods in the literature for that? So you face that problem I showed you before as a kind of toy model for another one which we are pursuing now, and I'm just finishing, Paco, just a minute more. And then the point is that you are considering quadratic functional energies like that, instead of considering the classical Einstein-Hilbert equations. You are considering these kind of problems here. And the idea is that if you make the Euler-Lagrange equation for that, you have some sort of fourth order Ricci Einstein tensor. You can see here that besides the Ricci tensor, which is the key part of the Einstein field equations, you have the D'Alembertian of the Ricci tensor, have a fourth order equation, which is the counterpart if you can make a parallel with CMC and Wilmore surfaces. This is the parallel with Wilmore surfaces in the sense that you have the Laplacian of the mean curvature. In that case, you have the D'Alembertian of the Ricci tensor. So this guy here is fourth order. The idea is to split that equation, roughly speaking, split into two second order PDEs. And these two second order PDEs are coupled. So if the exercise I showed you is an indication, is a hint that it's possible to manage with the equations like that, trying to split this fourth order general relativity equation in terms of a second order system of PDEs. So that's the real purpose. You have now, there's a program that's in construction with Rodrigo, Paul Laurent, and Nicolas Marc. And one of the ideas is to justify that that equation, A equal to 0, is physically relevant. So one of the things you just recently proved with Rodrigo and Laurent and Marc, it's that there is a very nice notion of mass for that. So this indicates that it makes sense to deal with that sort of equations. And that mass is linked to the Q curvature, which is the, say, counterpart of the scalar curvature for this fourth order stuff. So the results indicate that it's possible to use Host, Maxwell, and all of these techniques for that fourth order equation. So that's the program you have now to develop. That's all. Thank you so much for your attention and patience. And Paco.
Pancho, ya terminado.
Thank you. Thank you very much. Do we have time for few questions? So, is there any question? Well, I would like to ask you, because, well, perhaps these two theorems that you have shown almost at the end about, you know, far from CMC and near or next to C. How strong are the hypotheses in the theorem of existence? I mean, how strong is to assume that you have a sup and super solution?
Yeah, in fact, Paco, that hypothesis about the Yamabe variant and being far or near CMC is to prove that there exists super solutions. In that case, you can work a bit and show explicitly the super solutions. You can since you have some conditions on the Yamabe variant, you can start with a metric gamma which satisfies a nice condition like positive scalar curvature or no scalar curvature. So it's possible to change the background metric. There is an intermediate step. You start with gamma, but since you have that Yamabe variant with the right sign, you can change gamma to another, say, gamma tilde, which has a nice scalar curvature. And then that's the intermediate step you use to find the super solutions. And that's why you need to impose conditions on the global invariant Yamabe variant, sorry, of the metric. But since you have that, the super solutions are constructed. Okay. But you prefer to have that abstract formulation that in any case you have, whenever you have the super solutions, you can run up that program. But then you have two examples when this is possible, is effective, which is, I have to say, are very, very close to the results you have for the CMC case to the vacuum case. You are in the same direction. It's not very restrictive if compared with the results you have in the literature up to now.
Thanks. Are there any other questions or comments? Okay, seems not the case. Thank you very much, George. I hope to see you soon, virtually or in person. Well, in person is more complicated.
Hello to my friends here, Ildefonso, Madalena, Leonor, all of you. So it was a pleasure. Thank you so much for the invitation again. Bye.
Hi.